Okay, let's go. It's my great pleasure to introduce today's speaker, McCuller. Lee joined the Caltech faculty in 2022. Lee attended the University of Texas and got his PhD at MIT in 2015. And shortly,
PhD at Chicago.
Oh, what did I say?
MIT.
Yeah, sorry, I got ahead of myself. University of Chicago in 2015, and then shortly after joined the LIGO project, where he worked at MIT. And he had a pivotal role in realizing frequency-dependent squeezing at the LIGO interferometers, which is now operational. Caltech has a very proud history when it comes to squeezing. The idea that you could improve the sensitivity of an interferometer by injecting squeezed vacuum into the dark port was conceived at Caltech by Carl Cage when he was here working with Kip Thorne, and then in another milestone in the 1990s, Kip and Jeff Kimble and others had the idea that if the squeezing is frequency dependent, then LIGO can improve its sensitivity throughout its frequency band. So the baton has been handed down, the baton of squeezing from Thorne to Kimble to McCuller. He is now Caltech's big squeeze, so to speak. Today, Bill explain to us how it got done.
All right, thank you. So yeah, this talk I am speaking very largely on behalf of LIGO, of course, also on behalf of myself. So I have to give the context that this was a major group effort of a lot of people, but I had a wonderful privilege of being involved with it and really helping it come to be with everyone's help within the project, getting to work with wonderful people here at Caltech and collaborating between MIT, Caltech, and the two LIGO sites. It's been phenomenal. And so I just like to pose a few questions here to get you thinking what we'll be going through in this talk. How strongly really can we measure the mirrors? This was the fundamental question that staged all of these quantum measurement concepts and the history of measurement in a quantum context to begin with was highly motivated by gravitational wave physics. Is squeeze light the best we can do? Frequency dependent squeezing obviously does better. And then, just getting into future things, you can't put me up, junior faculty up in front of my peers without also talking a little bit about what this means for the future. So my roadmap generally will be an introduction. I carefully crafted my abstract of this talk to tell you how we get to the quantum noise limit, because that's actually the first extremely difficult step in the LIGO detectors, what it means and what it means for making astrophysics measurements. Some quantum optics, read that as squeezing. And then unpacking all the things that John was speaking of. What is this broadband quantum enhancement of the LIGO detectors? What is frequency dependent squeezing and how can we conceptualize it and think of it? And of course, how well are we doing with it? How is it operating in the LIGO interferometers? And then finally, with whatever remaining time, I hope to get to just some things where to go, like can we continue to improve quantum measurement using gravitational wave physics or gravitational physics. So this is the first view. This is the first time we saw frequency-dependent squeezing in the LIGO interferometers. I like to put these because this is actually what you look at when you're in the control room. It's of course difficult to interpret what's all going on here, and I'll walk through that later. But generally, you can see no squeezing. You push the noise down, and if you don't use frequency-dependent squeezing, it gets worse at some frequencies and better at others. So why is that? What does it mean? And of course, what does this mean for doing better astronomy using the LIGO gravitational wave detectors? And of course, it was a fun project. I visited the sites on many times, worked with many people to not only design many of the components and engineer optical paths and control systems, but we got to implement it. And that's really fun going into the detector. People enjoy the progress, seeing it come alive in a very rapid time so that all the astronomers can use it. So the context for this is gravitational wave science, which is a new kind of astronomy, really. So historically, astronomy is opened up and we learn more about the universe from it every time we can see new wavelengths or look at the sky in a new way. So, starting with an optical telescope and just seeing, oh, there's a lot more out there than the visible eye can see. What are those things? You discover new objects, populations of those objects that must have come about, and of course, what is the physics that drives those astronomical objects populations? And what can we say about physics here on Earth from those, and about our cosmology? How did the universe come to be? And until rather recently, this has all been driven by the electromagnetic force and electromagnetic carriers at various wavelengths that give you different images of the sky, different foregrounds, backgrounds, distances, and time periods. But now there's a lot more astronomy going on without using electromagnetic detection. So new modalities from things like astroparticle physics and of course gravitational waves. These modalities are called new messengers, multi-messenger physics, where you get complementary observations with the historic way of doing astronomy. And that gives you new information and ideally lets you, have correlations between measurements across multiple modalities. So you can really dig deep into the objects and learn as much as you can about the cosmos. And I will be talking, of course, about gravitational wave interferometers. So what are these? So this is to detect not electromagnetism, but actual waves propagating through the fabric of space-time from extremely extreme objects of space-time itself, black holes and binary systems, things where once they coalesce and merge, you can learn and test things about general relativity itself from the gravitational transients in space-time. And of course, when you find those rare neutron star events, you get to learn about the equation of state of dense nuclear matter that is extremely difficult to replicate meaningfully here on Earth because of how condensed and extreme the objects are colliding. And of course, these are populations of these, so now you get to ask all of the astronomy questions of how did these come to be, what are the dissipation mechanisms that could form binary systems, and how does that inform our cosmology? So how are we detecting these, and how did we start this process? So starting with going from the Nobel laureates here, the gravitational wave detectives. In order to make a project like LIGO and gravitational wave detectors come to be, you need both the possibility of making measurements that you can actually see something using some kind of detector and reach a sensitivity that is meaningful. And this would be the realization that gravitational wave, or that interferometers, Michelson type interferometers, were so inherently sensitive to very minuscule gravitational waves. And of course, there were others that had realized this idea, but you not only have to realize the idea that you can make a detector, but you have to think through every possible reason why it might not work. And that, of course, is what earned Ray Weiss the honor of his distinction. Likewise, you have to know that there are objects out there worth seeing, that are interesting to see, that they exist in enough of a rate that it is worth building such ludicrous detectors as gravitational wave interferometers. And so the science program driving that and thinking through the populations are out there, what the waveforms look like, how detectable are they in a signal processing sense. That's actually something that is incredibly important. That's both of these pieces have to come together, science case and the actual detector science. And then you have to build something. And so in this case, the two LIGO observatories, each one a laser interferometer with 4-kilometer arms. They're not just Michelsons, they're much more sophisticated than that. And they are at a considerable distance apart from one another so that you can triangulate on the sky the signals and get not just that a signal is out there, but where it might be. And of course, by using coincidence, you have a much greater case that what you observed is not random noise, but actually a unique detection. And of course, the ability to make that come to fruition goes to Barry Barish for driving that forward and navigating an extremely complex process. But the LIGO detectors are part of an observatory network, a global network of detectors. In this era, the advanced area of detections, primarily Virgo is contributing along with the LIGO detectors. But historically, the GEO 600 detector has been very important and formative in the technology development. All of the detectors have been important in the technology development. that actually has led to actual detection sensitive instruments. And of course, we have the Kaga detector in Japan, which is operational, but still not quite sensitive enough to contribute detections yet. And then LIGO India, which is, it's past planning. This should be some other color than that, but not quite yellow. So how do these interferometers work, and how do they make detections? So if you start from a binary system like black holes, they start in an in-spiral phase. So this is a figure from the first detection paper, the potatoes, people often call it. So they are orbiting each other. Because they are such dense systems, as dense as they possibly can be, they can have very narrow orbits. And so they can orbit with a very high period. So this is milliseconds, and they're going kilometers. So they are actually going large fraction of the speed of light. When they're doing that, they are bending the space-time around them, and they're bending it so much that it's actually able to radiate away. And that's carrying energy and decaying their orbit. So their orbit is actually shrinking, and as the orbit shrinks, their orbital rate increases, the period decreases, and that actually causes them to decay more energy faster. And so you get this characteristic chirp, where the frequency depends on the distance between them, and then the amplitude depends on the fact that their velocity is increasing. Finally, you get a merger phase where they touch in some sense, and then the ring down is kind of the gravitational transient of this intermediate thing. It's a short period where the black hole has some hair, but it very quickly loses it as radiation. And then, so this is kind of a picture of what the waves radiating are. The gravity is, as a metric, has a very particular character where it only propagates quadrupolar modes, which you can see is kind of this tube. So this is flying as a tube. If it's going straight down into the Earth, that's the circle of it. And as it flies down into the Earth, what it is doing is very fractionally stretching one of the arms and shrinking the other arm. And that's precisely the degree of freedom that a Michelson interferometer is very good at measuring at. And since it's a fractional change as a metric, that has to be turned into a displacement that you would measure using some wavelength of light. And so you need a very long baseline in order to multiply it into a meaningful amount of displacement. And so the whole game is, can you make a detector that can measure displacements sensitively enough to measure these extremely weak gravitational signals? Because as extreme as these objects are, they're so rare that they have to be extremely far away. And it's an incredible coincidence that our ability to see them is very, very well matched to their population. So as you're doing this, you're in some sense, looking at the spectrum of space-time, what's passing through, what's scattering off of these rare objects or emitted from these rare objects in space. And so this is actually an early catalog. I put this one up before the newest catalog because the new one is just so much larger. The rate that we're detecting events is increasing. And of course, this second catalog actually shows you fewer events. And the point to make here is that, okay, there's a good number. We're starting to get, they're out there. We get that. But each one is actually a bit of an individual. So it's not just that you're seeing events, but you're also asking, okay, well, this one is the most eccentric, or this one is the most, has the highest spin or the highest mass ratio. So you're actually collecting data about the entire distribution of the population, not just the fact that there are objects out there that are emitted. And of course, this is our first binary neutron star with the incredible distinction that it was followed up electromagnetically. So you could not only see, the masses and the characteristics from its waveform and do all of the gravitational wave tests, but you can also see it in the electromagnetic and say, how much was spewed out and at what rate did it decay, and what does that tell us about like our process, element formation, and the evolution of very heavy elements in our universe. So, but I work on the instrument, so I want to get into the aspects of this that are important for how do we make detections and how do we improve, namely the quantum mechanics of our detector. So let's talk a moment about the sensitivity of advanced LIGO and the kind of metrics that are important. So first is the spectrum here. It's kind of funny units in that it is strain, ASD is amplitude spectral density, and it has this per root hertz. So what you'd really like is you'd like to know how much strain can you see, like what's the standard deviation of the strain, or what's the variance of the strain. That wouldn't have the per root hertz on it, but you're measuring signals that are carried through time. So you need, a dimension of time in the noise in some sense. And if you integrate through this, if you have a signal and you form some signal to noise ratio, you can calculate from this spectrum exactly what various characteristic waveforms, what's the sensitivity to them. So you start with the spectrum, and that gives you kind of what's the frequency resolved density of the noise. And then you can convert that into an effective range out to which you can see. Or if you saw something at a range, what is the signal to noise ratio that you're seeing at it? And the kind of standard distances we're talking here is, we say, binary neutron stars are order 100 megaparsecs. Well, a parsec is 3 light years, so 100 megaparsecs is 3 × 10⁸ light years. It's large, and the event rate actually scales with the volume. So we're talking that these detectors are seeing things like cubic gigalight years of sensitivity. And so, yeah, very rare objects, but really astonishing distance to which you can see. And in some sense, even though it is the most physically intuitive metric, the RMS strain or displacement. So like if you were to say, if I just measured in this band like 50 hertz to a couple hundred hertz, what's the strain noise that you would get if you integrated them? That would be like the RMS strain or displacement. And so that's what you would mostly think about if you were just designing a physics experiment or trying to qualify what's the precision that the detector can see things. And that is kind of the starting point for thinking about how crazily strong we are probing the LIGO test masses. So if you look at this, so this is about 1 or 2 × 10⁻20 meters per root hertz if you multiply this tiny strain by the 4-kilometer arms. And if you integrate that up, that's kind of 2 going down towards 1 × 10⁻19 meters RMS. So that's like a standard deviation. That's an incredibly small precision. And if you're being really not careful with units, it's smaller than the square root of h bar. So wonder what the implications are there. And with that kind of precision, well, this is a kind of very disingenuous comparison with other realms of physics, but it is an impressive length scale to be able to see. You can see kind of almost to the edge of the universe when we're looking at the LIGO binary neutron star range or the binary black hole range. We're getting to within kind of a factor of 10 of the Hubble distance. And so could we get there? Could we see every event in the universe? Maybe, probably not with LIGO, but it might be possible, and we should go for it. But this is the way that we are able to see such magnificent volumes. And of course, it occurs because what we are seeing are such extreme objects that we can see them far away. So what's the fundamental realization that makes us able to make such a sensitive detector at the 10⁻20 meters per root hertz? Well, if you have photons in a Michelson, each photon in some sense makes its own independent measurement. We use 1064 nanometer light. So 1 over k, the wave number, is 1064 over 2 pi measurement, okay? So kind of 10⁻7 levels, 10⁻7 meters. So the minimum measurable length variance from counting these photons or measuring them is delta x, which is proportional to, statistically 1 over the square root of the number of photons that you measure. And so, there's a lot of photons in an interferometer. Even with 1 watt of light, you get about 10 to the 19, which would give you a spectral density, of course I changed units a little bit on you here, of 10 to the minus 17 meters per root hertz. So LIGO just needs to get a mere 3 orders of magnitude over that in order to be at the sensitivity it actually is. And this is a very classical picture here. Of course, the light inside a Michelson interferometer is much more like a wave than this, but it actually gets the right answer when you're not doing fancy things. Of course, LIGO does use fancy things, and so I'll point out Ron Drever's contributions here in realizing that cavities and trading off bandwidth, essentially modifying the density of states of the light so that you have a higher density at frequencies you care about at the expense of a lower density at frequencies where you do not care about, can give you further enhancement of the signal. So this is the practice of using arm cavities, which also enhance the optical power. So you just simply have more photons. And then you can do a series of tricks to greatly enhance the power up to a megawatt, nearly a megawatt. And we are currently at about 350 kilowatts on our way. And then you can use the signal recycling mirror, rather signal extraction mirror to get the bandwidth exactly right, kind of optimally for the detection of your gravitational waves of interest. And of course, you actually could really push on the sensitivity. And amazingly, we actually have to make the detector slightly less sensitive than we could because of that 10 to the minus 19, the trade-offs, the fundamental trade-offs in measurement theory that I'll talk about. So what, that's all great. You can design an interferometer, you can make it profoundly sensitive, but you have to, in a quantum mechanical sense, but then you actually have to get there and do that. And that's kind of the remarkable aspect, and years of research here at Caltech to basically engineer every piece of the system so that you can hit the quantum noise floor, or at least the most fundamental noises below. And the way LIGO does that is that it has an active inertial isolation that takes a one-ton stage and makes it as stationary as the best seismometers that you can buy. Then it uses a quadruple pendulum that starts at about 1 hertz and then gives you 1 over f to the 8 suppression, so that by 10 hertz, you're at 10 to the minus 20 meters per hertz. And a clever thing about this is that, yes, it's a quadruple pendulum to get that level of suppression, but you see the final 2 stages are not made of metal. So it makes sense that you need a glass mirror somewhere, but the stage above it is also glass, and then the fibers carrying it down are glass. And that's because you are limited by the Brownian motion of the materials holding up the test masses. If you put it in space, you wouldn't have that noise, but you have to do it on Earth. So we use a combination of gravity, which is lossless and does not contribute Brownian motion, and a very good material, glass, with a Q of 10 to the 6, and it dilutes it to have a Q of 1 billion, which is a 2-week ring down. And when you have that, fluctuation dissipation theorem basically doesn't have a whole lot of dissipation to pump back in as noise. And so this is how you can get such a subdominant contribution from the suspension Brownian motion. However, the next most fundamental noise is this red one, and that is the same effect, the vibrating of molecules, which you can compute entirely through fluctuation dissipation from the material properties of the optical coatings. Basically, if you press with light on the mirror, the conjugate action is that it will move in displacement. And so if there is a dissipative loss in there, it will drive noise into the displacement of the mirrors with this spectrum. And so it's an ongoing research to find materials that can suppress that noise. And then the quantum noise, which has this funny curve. You might expect for shot noise, it would be white and flat, but it's moving up at high frequencies due to the fact that we use cavities, that we're trading off density of states so that we can get more sensitivity at low frequencies than high. But then at low frequencies, you have what is called radiation pressure noise. And this one is rather fundamental and a major focus of what I will be talking about. So, these are the two contributions. And so we lose sensitivity because at about 450 hertz. And then what is this radiation pressure noise? Well, in some sense, you would expect it has to be there. So we are measuring the mirrors of LIGO. We're measuring their positions of 4 mirrors. We could call that X. And we're measuring it at one time, but we're measuring it continuously, so it's some time later. And so we're also effectively measuring the velocity of these mirrors. And that's curious because we're measuring the position incredibly precisely, and we're also measuring the momentum via the velocity. And it seems like you should not be able to do that. It was actually work originally realized by Babinski, and then through a lot of collaboration with Kip, thinking through what the implications are of this in terms of gravitational wave detectors. It was realized quite early that this would be a fundamental problem, that you're going to stress this through this kind of argument. Now, this argument isn't totally complete yet because this is making independent measurements through time, like sampling. That's not quite what LIGO does, but you can convert it into a frequency domain kind of representation, and you would get that there's a fundamental limit that is one of the SQLs, the standard quantum limit for measuring a harmonic oscillator like a test mass. And this, you see the LIGO curve touches it, and it goes up higher at low frequencies and can't surpass it. So if you change the power or the probe strength in LIGO, you can move this, you can move where this knee touches this curve up and down, but you can't go underneath it, seemingly. And this, of course, historically has been very important in the theory of quantum measurement. So this is kind of the first realization from Brzezinski, and then distilling this into the implications and what it means to make measurements that surpass this. Like, how do you do it? How do you prepare states? Ultimately, it's because the thing that you're measuring, x, does not commute with the Hamiltonian. That's distilling it down a lot. But and there's many ways you can just make it commute. That's one way. But you can also do it through state preparation. And these at the bottom are interesting simply because they kind of resolve the conundrum of how you can do better than this through a very different means than all of the others. And frequency-dependent squeezing is a little bit of both. Frequency-dependent squeezing was first realized here, but not with that name or in that form. So Unruh realized it, but nobody knew how to actually make the states until Kimble. So, kind of to summarize, interferometers measure the position of their mirrors X using optical light. So it's the light here that must somehow be the responsible party for the noisy consequences of uncertainty, wave function collapse, or rather projection is maybe a better word to use. So it's the quantization of the light that's enforcing this for these continuous measurements, and that is producing the standard quantum limit. So there are other physical pictures to utilize to talk about how we might go beyond this limit. And one of them is to say, well, what is radiation pressure? So if you have light coming in, it's got some amplitude of it that's impinging on the mirrors. The light carries momentum. And since it reflects, it has to impart that momentum upon the mirrors. And there's this picture where light works like photons, so there's a shot noise associated with it. So we'd expect some sort of force noise due to the light punching the mirrors with its sidebands. And that gets integrated up into displacement through the fact that the test masses are nearly free in very, very low frequency pendulums. And that creates the phase noise. You're trying to measure that phase noise as that's where the information about the mirror's displacement and the gravitational waves is. So the fact that an amplitude fluctuations from shot noise are creating displacement noise or phase noise is kind of the reason you have radiation pressure noise. And that's why it's 1 over f squared is the integration of force to displacement. So a nice kind of intuitive picture of these photons. And as you increase the amount of light, you of course increase the number of photons, you would increase this force noise. And so everything kind of checks out that there's a trade-off. More light means more photons to get better phase resolution or sensitivity, but it also means more force noise, distributed between phase sensitivity of displacement and amplitude noise of the light. And I'll talk a little bit more about those. So the two pictures kind of correspond between a fundamental measurement problem that just is entirely abstract and what the light would be doing to the test masses. And to talk more about it and kind of speak to one of the resolutions of this problem, I have to describe squeezing. So, well, squeezing is a very interesting, nice technique. In some sense, it must be complementary to increasing the amount of light in the interferometer because it is increasing the phase sensitivity, the probe strength, or it is reducing the standard deviation on X. So you would expect it to have some sort of trade-off in radiation pressure and some sort of measurement trade-off fundamentally from this Brzezinski argument. And we installed it in 03, observing run 3, the one just before the one we are in now. And we saw many improvements. This is also true in the going to 04, things like the power level is increased, background scatter. The duty cycle actually was probably quite important in getting more events, coincident events. The grounding of the instrument was important, just the amount that 60 hertz leaks in and creates sidebands. Laser noises, a lot of control systems, which create a lot of low frequency noise. And of course, people don't ever mention, but just the glitch rejection and data analysis, I think also contributes meaningfully to the number of events. And so the detectors have become very impressively quantum limited by 03, which means that it's a great time to improve their quantum sensitivity through squeezing. So in this case, we went from 120 megaparsecs to 140 by turning on squeezing. If you cube that, you get something like a 50% rate increase on top of everything else. And so this was done. And this stark increase is the fun one that's cited. And I don't know that we've seen one yet for 04, but I look forward to that. And so how does squeezing work? Well, light is, in fact, quantum. Here's a picture from one of the nice videos that you can watch on how an interferometer works. And of course, it's the light waves going back and forth, interference. You use that as a proxy, the amount of power leaking out as a proxy for any motion at the end mirror. So, okay, so this wave though, well, at every moment in time, there's actually something like a wave function associated with that. It's just second quantization. And here's the picture that depicts this. So this would be the wave, very sharply defined here, but actually has uncertainty. And it looks like a sine wave because this is a coherent laser. There's some amplitude to it. And as it evolves with time, with its harmonic oscillator evolution, it's, you know, it's a sine wave. You see what's going on. And this in the phase space picture, so if you measure it here versus pi over 2 phase away, then you're making the two projections of these two measurement quadratures. So in one case, you would call it the phase, and then one the amplitude. Of course, they're equal here, so it's hard to just, you know, say what am I talking about between them. But in this case, where it's high, where you at the peak of the sine wave, you would define that as the amplitude, and then right between as it's crossing zero, you would define that as the phase quadrature. And of course, the definition is rotating depending on where you are in the light or at what time you are at. But then if you do something like amplitude squeezing, you're actually changing the wave function of that sine wave at every moment of time. So its evolution is, of course, rotating it through a sine wave, but it's also changing the wave function itself, the distribution. If it starts as a Gaussian, it will stay as a Gaussian. But if it starts as a narrow Gaussian, it has to widen, because after you go pi over 2 phase, you're actually taking the Fourier transform of it. And so it will alternate between squeezed and anti-squeezed, between the amplitude and phase. So this also must be true because the two quadratures of light are conjugately opposite variables, or and so they have an uncertainty relation. So if you reduce the uncertainty in one, you must increase it in the other. And this you are just directly seeing. And then of course you can see vacuum where there is no amplitude. So you it's difficult to intrinsically define the phase because there's nothing to define it. And by default, it has equal uncertainty in both, and it's a circle in this phase space. And then vacuum squeezing, where if you squeeze it in, say, the phase quadrature, it will alternate and then be anti-squeezed in amplitude and vice versa, depending on the phase that you're measuring. So these phase space depictions are actually very useful, but this is kind of the physical intuition that goes with those. And I like this. So this is my favorite applet in 12B for showing this, where if you use a quantum harmonic oscillator and then you drag the cursor, you can create a squeezed but offset, a displaced squeeze state. You can watch it evolve. And this is going between this state, which it's a little too narrow, and this one where it's crossing zero, but wider, and then back. And you can just see it bounce back and forth. So that's fun. And the bottom, so this is the harmonic well, this is the actual wave function that you're looking at, and this is the complex, or the conjugate variable that you might be projecting. Now it's just fun. And then the bottom are the energy eigenstates. states. You see, I've squeezed it quite a bit because it's occupying a lot of energy eigenstates. states. So what does this mean for gravitational wave detectors? What was the realization that you could use this in an interferometer? Well, as mentioned, this was Caves, quantum mechanical noise in an interferometer, 1981. So it's the leap that, even though you think of the state of the interferometer kind of being driven by the laser, that's not the state that's actually influencing the measurement. And that's because the vacuum goes into the interferometer. So typically you operate these at what's called dark fringe, where very, very little light comes out, only a very small amount that lets you see modulations of it to detect gravitational waves. So almost everything reflects off of the interferometer. In fact, most of the laser gets reflected back to the laser, and that's how we make a cavity that generates so much high power in the arms. So here, what you do is you replace that state. What's going in by default is the vacuum state. It just reflects off, and that vacuum state is what sets the measurement. So as a gravitational wave comes, a more modern interpretation is that it is just displacing the wave function of the light at each moment by an amount that's proportional to, whether or not the gravitational wave is high in amplitude, positive, negative, or zero in amplitude. It's displacing it. And it's only displacing it in that phase quadrature, because that's the quadrature where you sense a shift in a length. So all of this you can change some of the definitions, but in this picture, that is the convention chosen. And so your ability, what you want to do is you only get one measurement at each moment of time. So you would like the best resolution possible to see those tiny, tiny displacements. And of course, with squeezing, you can do that. If you're only measuring one of the two quadratures, let's reduce the uncertainty in one of them at the expense of the other. That's great. So now you can resolve the signal and see a signal, see the gravitational wave better. And of course, there's other ways of thinking about this in physics. So we use a nonlinear Chi2 nonlinear crystal, and that in some sense just generates a 3-photon interaction through the nonlinearity, and that causes multiple processes to occur. So there's emission, where a double photon spontaneously down converts into 2 pairs. There's upconversion. If you use the original light, you can create the second harmonic. We use that as a tool, but not as a quantum technique. And then there's down conversion, where you can mix a second harmonic frequency with a lower frequency, and it will create a partner that is frequency offset with this alternate frequency relation. It gets mirrored around the center frequency. So all of these things are happening. So when you talk about squeeze states and you say that they are photon pairs, that's this process occurring. But when you talk about squeeze states in terms of dBs and the ability to improve a measurement, that's this process. It's actually the vacuum sidebands going in, experiencing this, and then getting mirrored down that causes the squeeze state. So this is a frequency domain picture, a sideband picture, which works great with ladder operators. But to convert it back to amplitude and phase quadrature operators, you need a conversion that was really described well by Kay. It's called the 2-photon formalism, and that gives you this nice phase space picture as a function of frequency. So I stop using a single phase space or a phase space as moments in time, and I stack them. And going into the page are different measurement frequencies, which is useful to talk about. And so how do we actually do this? We use a Preskill optical parametric amplifier. That's our nonlinear crystal, driven by the second harmonic, in this case, 532 nanometer light. It's in an oven, phase matched, phase control. Curiously, it's in a bow tie cavity. This is a bit unconventional. And the use of a cavity strengthens the interactions by trading off density of states. But the fact that it's a bow tie and it's a traveling wave cavity is really useful for LIGO because light leaks from the interferometer to this device. And it's very, very easy to make the interferometer worse than better, even if you have a fancy technique like squeezing. So you have to engineer, you have to do a lot of engineering in order to make even your fanciest quantum techniques applicable to a gravitational wave detector. And this was one of the key ones, is isolating backscatter. This is a cool picture of what it looks like. And a review. It's actually a long history of the development of these and pushing down into the gravitational wave band. Actually, Jeff Kimble did one of the first crystal squeezers, not the first squeezers, but the first nonlinear crystal squeezers, and got kind of like 5 MD. It's actually not bad for any attempt, much less the first attempt. So yeah, that's now 3 decades ago. And only now are we really realizing it in a way to enhance detection. And I mentioned this trade-off, and that as you inject squeezing, you're actually going to increase the probe strength, and in some sense, you are intrinsically going to have to make it lose some sensitivity at some frequencies because of the injection of momentum uncertainty. That is the process of demolition that was used, and non-demolition, the avoidance of this deleterious measurement process. And this paper is the first practical realization of doing it for a gravitational wave detector. And yeah, many of these people still around. In fact, Max Go is at JPL that I met a few weeks ago. So that's very cool. And how does it work? So here you have to change from this cartoon picture of particles, individual particles, punching the mirrors, and you have to think in a coherent quantum picture. So again, we have amplitude, force, displacement to phase, that sequence. But now, abstractly, you have 2 quantum operators, A1 and A2. A1 would be amplitude, A2 phase, something like that. And when you pass through the interferometer, there is some coherent coupling that is transforming the optical phase space. And it's because, if you eliminate the interferometer from the process, there's just what goes in and what comes out, and what's the transformation that occurred. And in this case, it's this matrix. This K is a frequency dependent conversion of amplitude into phase due to this process. So it includes the susceptibility of the test mass, which is basically just 1 over omega squared, or 1 over m omega squared, and factors related to the amount of force that is imparted for a given amplitude on the light. And that is going to scale with the power. So if you increase the power, K gets bigger. If you make the test mass lighter, K gets bigger. And K is bad because it's what's creating phase noise. So what does that look like? Well, if just standard vacuum is going into your interferometer at every single frequency, again, we can transform into the frequency domain from the time domain. Works perfectly fine with your quantum operators because everything's so linear here, luckily. And what's happening is as you go through the interferometer, this sequence occurs, you get this transformation. This matrix is a shear matrix. So what happens is when you are somewhere far out on amplitude, it is being converted into phase. And so K is small at high frequencies, nothing happens, vacuum in, vacuum out. So your measurement, not affected at high frequencies. At low frequencies though, K is very large due to the integration up of force into displacement. And that's creating this very strong shear. So if you turn your head, that's squeezing. Like the interferometer is squeezing. This is kind of the realization, oh, you can actually create squeeze states from mechanical systems. And it's through this process. Of course, where is it squeezing? What's the angle? A bit funny. So you have to be careful with that. But if you're purely measuring phase, it's bad that it's squeezing because it is more what I would call anti-squeezing. It's increasing the noise envelope in the quadrature where your signal is, the phase quadrature. And if you inject squeeze states, here, this process still occurring, it's just that your states occupy a different distribution in their phase space. And the shear is really particularly bad. So this is the explanation why, even though squeezing is improving the probe strength, making your delta X smaller, ultimately you are undermining your sensitivity at low frequencies and for very heavy gravitational wave systems because of this modification of the optical phase space and the increase in noise at these frequencies. So the clever way to do this is don't inject the same squeeze state at every frequency. Let's inject a different state at different frequencies, and namely, let's rotate it so that where you're getting the strongest shear, it's simply unshearing it back towards the vacuum. You can actually retain it still being in a squeeze state. And this is the basis of frequency-dependent squeezing. Kind of realizing, taking advantage of the fact that we say squeeze states, we think like, oh, it's the same thing at every moment in time. But you have the freedom of defining what basis matters to you, frequency basis in our case. And in that basis, every state is independent. You can modify it to your liking. And in our case, you just have to figure out how to do that. And that was the KLMTV, the Kimble paper, was the realization how to actually build a device to do that. The way to do this is, okay, you've got your squeezing system here. Normally, you would just pump that directly into the interferometer. But instead, let's put an optical cavity in between. And here, this is a Faraday isolator. What we're doing is we're just using it as an optical circulator. So that light goes in, on its way back, it gets redirected to the interferometer. Likewise, at the interferometer, it gets directed back and then towards the detector. And this cavity, when it is off resonance, it modifies the sidebands. So when it's differentially, so it is what's called an all-pass filter. It applies a phase shift, but ideally does not lose any of the actual light. And so you are differentially changing the phase relationship of the upper and lower sidebands. And that phase relationship is actually what determines what the squeezing angle is. So the realization, oh, if you use a properly detuned cavity, it actually matches with the optomechanics perfectly to cancel and create this broadband enhancement. That is the notion of using a filter cavity frequency dependent squeezing. And these are a couple of citations for actually a worldwide research effort, and of course, very targeted development for LIGO to do this in gravitational wave detectors. So after first paper came out, there was a first check. Yes, the physics is sound. You can modify the squeeze states. You can just see the fact that squeezing goes to anti-squeezing through a resonance in an experiment. Of course, this is all at very high frequencies, so it's not immediately useful to a gravitational wave detector, but it shows, yes, you can do this with a cavity that works as expected. And then at my previous group, the first experiment doing this at 2 kilohertz in a 2-meter cavity showing that you can rotate into the acoustic audio band and that it works, and there's not too many issues that you might expect to ruin your gravitational wave detector. And then I worked on this one, a 16-meter cavity, somewhat diabolically difficult to operate because it was both long but very low bandwidth, so that it would drift like 18 megahertz per second from pendulums, but it was only 60 hertz. So like seeing that you were ever even aligned was tricky, things like that. But a fun experiment once we got it working. And this experiment and this one were to show that you could actually do it at kind of the 50 hertz crossover bandwidth of a gravitational wave detector. We learned a lot from this because, yeah, there's a lot of subtle issues that you might realize, and a number of them we accommodated for in the LIGO design. And so, it's like here is from there. Even before that experiment was totally done, but we had seen it work a bit. We kind of had to commit and say we're going to do frequency dependent squeezing by 04, not wait for the full A+. And there we go. This is the site's installing a new, these are the actual arm tubes, a couple decades old. Here's a new cavity for the 300 meters. And what's inside there, inside these chambers, is a lot of components. So we start with the squeezer, we relay it around through telescopes that make the beam large enough for a 300-meter cavity back, and then through a bunch of Faradays in order to get the backscatter isolation. So it's kind of tough because this is a very high finesse cavity. And so it's very easy to modulate any light into noise that will mask and destroy your gravitational wave signals. So along with that, we had to enhance it or add in new hardware developed at a number of places. University of Florida, McCuller, Caltech, and MIT, to basically to get the lowest loss possible so we get as much squeezing as we possibly can. And integrating all of these optical elements to optimize for that took very specific design that had not really ever been done before, and is proving that we can do it and make it even better in the future, hopefully. So this is just some of the technology. Some of the realizations from 03 was that there's actually we actually are learning a number of things about squeezing from the interferometers that no one had ever seen or realized in university labs because the interferometers are so complicated. So namely, very multi-cavity effects. So what actually does it look like in advanced LIGO? So this is now the publication, the main plots. So at this stage, we are getting 4+ and 5+ dB. I think now we're hitting more like 5.5, yeah, max 5.5 in the Livingston and Hanford detectors. So that's pushing the noise down a huge amount at high frequencies, where you're looking for all kinds of interesting features of gravitational wave signals. Maybe by that point, by those high frequencies, you've detected them, but you would like to extract as much out of them as you can in order to know what it is that you are seeing and the features, the parameters about it. And then at low frequencies, you see, if we were to inject standard squeezing, this is actually radiation pressure plus a little bit of bad cavity stuff going on. It's larger than it should be if you're looking closely. But you see that it's a huge increase in the noise. So we would have been limited to about 160 megaparsecs at the best. In fact, as we turn up the power, we have to turn down the squeezing if you don't have this technique. But then you turn on frequency dependent squeezing, you win at all frequencies. You're actually, we haven't proven it, but the detectors should be operating sub SQL now while they are making detections. Now, not fully sub SQL, like the noise goes below the knee, but the quantum noise contribution is actually beating the naive limit from the Brzezinski type arguments. What is the standard quantum limit? So this lets you see events earlier, early detection. It lets you see much heavier events. And for all of the other events, you're getting much higher signal to noise. And so, and now you simply don't have the trade-off. So you can keep pushing on the detector and keep increasing the power, increasing the squeezing without the limits, without the trade-offs that you would otherwise be facing. So ultimately now we're actually hitting 170 megaparsecs at Livingston at times. And it's greatly improving the detectors and all of the science that is coming out of them. So actually the least impressive metric is simply the in-spiral range, which is increased by like nearly 20%, giving a 60% improvement in the range with this technique, or a 60% improvement in the detection rate. And of course, I have to say, this is one triumph among very many in LIGO. Like the fact that it all can come together, you know, the amount of engineering it took was a lot, but it's built on LIGO, which is a phenomenon to exist in the first place. So it's been a great privilege to work and continue to work with LIGO to improve it. So, and I guess the final point is, you know, this is all fun quantum mechanics that I talk about and give a nice picture of, but to actually make it real, you had to make the detector entirely better and not worse anywhere is the whole point. So this ultimately, the research, the implementation was about instrumentation, experiment, making a system that is incredibly interesting, or a physical process that is interesting, work for a real experiment and project. And these are the plots that say that it is not injecting noise. What's called the backscatter is well below the DARM by about as much as I had hoped, maybe not quite as much, but it's incredibly small. So this is, though technical, is actually, I take great pride in. So let me just mention briefly where I have to go. A couple of future science directions. So squeezing is this extremely powerful resource in LIGO and beyond. We should continue to develop it. But you know, now we've used a very powerful technique. It may require incremental advancements, but we should use it as a resource for new applications, things like continuous quantum variable information and things like that. That's an incredibly nice use where you can work with squeezing and implement new things out of it. By getting very high squeezing goals, you can suddenly have a transition where it becomes useful for computation, things like that. Gravitational wave instrumentation touches on many new technologies, thermal noise from two-level systems. Materials are what make detectors. So that's the next limiting thing in the quantum noise. So we need to continue driving the study of material science. Can we bring, gravitational wave instrumentation closer to industrial quantum information technology? One thing, for instance, that Ron is working on, using silicon technology to make gravitational wave detectors. And then, LIGO is a great example, often cited now as a quantum sensor that's being enhanced with quantum techniques. Can we use that to make new kinds of quantum sensors? It's operating at a huge scale and yet at the quantum limit. Most technologies seek to miniaturize, use lower masses, but great sensitivity. So they might end up limited by mass. Can we use these techniques on micro devices? And what I'm interested in is, what new fundamental physics are opened up as we develop these long coherence time technologies, like things that are useful for quantum computers. So how can we use that? And in particular, how can gravitational wave astronomy drive this? So I don't think I have enough time to talk fully about Cosmic Explorer, but it's a next generation set of gravitational wave detectors, substantially about 10x more sensitive than the LIGO detectors. And that basically puts it out to see all events out to the horizon for binary black holes well past what we expect them to have first formed. So we'll see all of them, or nearly all of them. And to high signal to noise. Binary neutron stars, it's going to collect a ton of them, almost out to before they exist, and at decently good signal to noise ratio. So that's the science case is still being developed, like the instruments in the science case and the motivation to say we should take on such another large project, still being developed. It's important to be interested in it and know how it synergizes with all of the rest of the astronomy community. And it will use, it pushes in all these technologies and gives us like interesting research motivation to keep working even on LIGO. So this is important. But, what are, historically, signal processing has been deeply tied to the generation of gravitational wave detectors. Squeezing kind of helps all signal processing, generically helps all signals and sensitivities. So here's kind of the different regimes of signal processing between coherent and incoherent. And there's a great science case that people are thinking about in neutron star physics. Well, they're kind of rare, that's not great. And it takes numerical relativity to even think about them. So that's challenging. It's hard to predict what these waveforms are because of this. So this is talking about this post-merger piece. So you get the merger, and then you see this ringing from what's called the F mode, like a quadrupolar mode or a dipole mode, rotating very fast in the remnant. And you can get a signal up here, but it's very weak. The strain energy of this thing is 10 to the minus 46 seconds. I know that's funny units, but you can directly compare it to the strain spectral density of a detector. So even though it looks big here, that's kind of in a lot of publications, it makes it look detectable and large. It's kind of a trick of the way they plot the units. This is small, so that's SNR of 1 at 30 megaparsecs. That's a very rare event. Even in Cosmic Explorer, it's going to be rare and weak. And, so this is a new piece here that lives in a funny place in the plot. And it's kind of going to intrinsically require event stacking to do it, to collect enough events to get a meaningful amount of SNR. And it's kind of an incoherent thing. It's very hard to predict. Are we going to be able to do the kinds of event stacking that we would like? Like, are we going to be able to coherently add multiple signals to look at them? That's debatable. It might only be that we can add them coherently, incoherently. And that has a huge penalty in the ability, like once you get below SNR of 1, it drops off very fast. So even though we sense so many binary neutron stars, the majority of them actually will only get an SNR of 1 in like a part in 1,000 of them. So is there a new kind of way of doing signal processing or measurement on a gravitational wave detector to take advantage of this? And well, I don't think I have time to actually walk through this example. I made a little numerical example to show, if you're trying to see coherently a coherent signal, you can easily detect the mean by stacking up, say, 100 events. If you try and do this with incoherent signals, you're trying to distinguish a Gaussian from a slightly fatter one. It's just intrinsically much harder. Like informatically, it's more difficult. And so, and that's using the standard signal processing that we do today. And there's just various scalings such that even after 100, an SNR of 1.3 single event detection takes 100 observations to get a statistical SNR of 1. It's a painful scaling. However, this is a thing that greatly motivates me. Why is it that LIGO talks about quantum noise and like no other high energy physics experiment or astronomy experiment? Why are they not talking about quantum noise? It's because they measure photons, they measure energy. We measure field, signal. So we measure the wave function in a way where we see the fluctuations. And if you measure energy eigenstates, you don't, because if there's no signal, there's no energy, there's nothing to see. And so there's only one outcome, no photons. If there is a signal, you get photons. So if you work through this, you would say that even though your signal noise is pretty bad after 100 measurements the same way, you would get actually, with an SNR of 1/3, like 2.5 photons. That's a pretty meaningful signal compared to exactly 0. And so you can have very high significance in that. So I think this is a regime where we could better improve incoherent signal detection, in gravitational wave detectors, although it's going to be a road to get there, because there's a lot of photons in gravitational wave detectors. And you look, there's a lot of lines, like the coherence time you need in order to do things like this. Cavities are not going to get you there. What you need is to be able to directly see signals come out and store them into quantum memories. So here I use atoms. And so you're storing multiple event components into various spin states of atoms. And then you can do a readout to get the photons. And if you have this device, you can operate it backwards and you can quantum enhance it at the same exact time. So this is the kind of device that I think is very interesting to develop. Now, again, like for LIGO, you have to develop the science case, the astronomy, the reason to do it. You have to develop that it will improve the measurement outcomes, and that it's possible. I think it's very possible to make this. A number of pieces of it have been demonstrated, but this obviously uses a lot of the components that people are developing now and combines them together for a very interesting astrophysics objective to study dense nuclear matter in a way that you basically can't study any other way, through neutron stars. So this is kind of a long-term goal. In the meantime, my group is coming together, and we are pushing on photon counting and using different technologies, more accessible technologies, to show that you can sense very, very weak signals in more standard interferometers today. And so we got a little bit of lab space just like a couple months ago, already filling it up to develop these experiments, waiting full lab space, and actually a number of people in the group all working. So altogether, thank you for listening. Going from many years of development of this technique, showing that it works and is productively improving astrophysics, and starting to ask the next questions of how we can keep improving gravitational wave detectors and quantum measurement using clever measurement techniques. So thank you.
immensely. It's very exciting to see that trajectory from early ideas to a real instrument and now actual science coming out. And thanks to your lucid explanation, you didn't put the audience under too much strain. Probably there, I'm sure there are questions.
Oh, I meant to pull out my balloon. I did bring it there.
All right, I'll ask one. So in principle, less loss means you can get more squeezing. So is that what's limiting you to, 5 dB? And what's the best near-term path to reducing loss and getting more squeezing?
Right. So it is the limiting factor. The other one is phase noise, where the squeeze lips kind of jiggles. Loss mixes in vacuum, standard vacuum. It takes a pure squeeze state and makes a mixed state that is, in some sense, fattered. And so that reduces the squeezing level. So the way to improve that, it is limited by loss by tens of percent, like 20 to 30%. About 20 we understand, another 10 we don't. And we think that this is actually, a lot of it is just intrinsic to the interferometer. And in fact, a lot of the people working here work on ways of making the interferometer better able to accommodate the colossal amount of power we're trying to pump into it, which degrades it in all these ways. So actually now we're trading off between improving it the classical way and improving it the quantum way. And the way to do that is through a fair amount of technology development and engineering on the detector to better compensate for all of the high power. So basically improve thermal distortions. The great leap forward way to do this would be to switch to materials that don't have this problem, like silicon, things with higher thermal conductivity, and that would be incredible. So that might be one way if we say, oh, actually, there's no point in going fully to a megawatt, because if we go from 400 kilowatts to 800, we've degraded the losses so badly from interferometer effects that we lose more squeezing than we gain. We go from 6 dB down to 2 dB, even though we're only increasing the power by 3. So we're kind of hitting this wall now. That's actually, I would say, one of the dominant things. A lot of the individual components outside the interferometer, we will keep doing, but that's going to give us like percent level gains here and there. Getting like tens of percent gains is going to require a lot of careful operation of the interferometers.
Question?
So if I understood it, you were saying that the photon counting technique really just only helps you with the highest LIGO frequencies?
Probably, like it will, there is a limit where so you don't see any photons, ideally, but all of the other classical noise do kind of bubble them off thermally. And so there is another kind of classical noise limit. This is like the background count rate in a rare process physics detector. Like what's the background rate from impurities of, your giant volume, like things that mask dark matter, stuff like that. Like the thermal noises of the LIGO detector will bubble off photons that way and put a new limit. But yeah, it needs more study. I'm not going to say that it can't be done, but in some sense, if we could just remove coding thermal noise somehow, then yeah, it could actually help even more at low frequencies. But it's also the science case changes, like it can't really help with detections. What it can help you with is like trying to do like really deep, strong test of general relativity, where like unmodeled test, where you can't maybe assume that you get you can't coherently stack the traditional way, because your test is so unmodeled that you don't want to assume, a waveform that you could stack up. So it's like a really nuanced discussion actually, but the post-merger case I think is strong. To be seen, needs more study, but I think that's a relatively strong case.
But possibly the photon counting strategy could also be helpful in other settings where you want to detect the stochastic signal.
Yeah, so this is a plant. So I'm working with Catherine Zurich on a quantum gravity experiment named GQuest, and that's a purely stochastic signal. It's extremely small, like in power units, 7 orders of magnitude below the shot noise. And there, like this trade-off is very stark. And so by switching to this, you can accelerate the experiment like several orders of magnitude. in speed. Just using even today's technology, if we switch to this fancy thing that I showed, you could get another order of magnitude on it. But yes, no, the near term, there's like multiple ways that you have to tackle this problem, because doing it is going to be difficult in interferometers, because a megawatt is a lot of photons and a shot noise is not a lot of photons. So that's the brief.
I have a question. So you're measuring on the dartboard of the interferometer, you're measuring tiny displacements in squeezed vacuum. So I'm wondering how sensitive are you to any amount of weak light from your interferometer that's like not properly mode matched? You have like hundreds of kilowatts circulating. If any of that hits your detector, does it come out of the squeezed vacuum?
So it's all at zero frequency. It's all at the carrier. So it's not, as long as that little bit of light doesn't get modulated the same way that the gravitational waves are carried on modulations, then it's no problem at all. And that's because we filter it. We have this fancy thing called an output mode cleaner that removes it as a light source, but it can't remove it if it gets modulated into our visible bands. And so this is it creates what is called backscatter. Basically, not only are all of the core optics on all suspensions, but everything else also has to be, because if it moves, it does this modulation. That's a problem. And that's why we had to do all these tricks with the filter cavity and engineering it with all these Faraday isolators and put it on these crazy suspensions. Is because even though that little bit of light is actually 90 dB down, 9 orders of magnitude smaller in power, getting to that cavity, that's enough to see it against quantum noise. So yeah, it's not necessarily a problem, but you have to strategize around it, and that's a lot of the work.
Alexei?
This is a very elementary question. You showed this picture with oscillations and the squeezing in this oscillating picture.
Yes.
Do you actually impose periodicity on your signal? I mean, do you measure?
How do we measure only one quadrature in some sense?
So you're losing some information from the inputs.
No, because well, yeah, I guess when it comes out, yeah, it's a good question. The modulation kind of will only be seen here, but when you make a beat note with what's called the local oscillator light, you basically are only ever measuring the wave function at this moment and this moment and this moment, because that's when your reference field is aligned in phase to create a meaningful amount of power. So the way that phase modulations on this light get converted into power modulations at the readout exactly selects for the phase of interest, like the phasing of this wave that is carrying the signal. And that's in some sense why our readout is called homodyne readout, and not, even though we're measuring photons, the actual measurement is measuring the wave function of the light at this moment. And it's because it's using that local oscillator field to do the measurement.
May I ask more precisely? The signal, if you do the Fourier transform at each frequency, there's two real components.
Mm-hmm.
Do you measure both real components?
Oh, yes. In the signal processing, yes. That's right. And that's yes, we do. And that's because what comes out is just a time series, right? So there's two quadratures of light. We measure only one of them, and we get a real-time series of that. And then you can do your signal processing. Well, it's actually done usually in the Fourier domain. But yeah, you get both components, both the real and imaginary components, because you are the one actually doing the data analysis where you integrate through a sine and a cosine that time series. So yeah, you get both of them. But the fact that there's two quadratures of light and two quadratures of a measurement, like at some sideband, is actually why this two photon formalism is very confusing. This conversion is tricky because there's kind of four things that you have to manipulate between.
Well, I would be more happy with plus. Four is the right number.
Yes, that's right. Yeah, and so in upper and lower frequencies and two quadratures. Yeah.
I see.
Yep.
Yeah, thank you.
All right, I think it's time for this event to bring down.